In this example, we're going to illustrate the principle of virtual work applied to a plate. We have a plate, and the Cauchy stress is given with this matrix. The stress at every point inside the plate is given by substituting the corresponding components or the corresponding position of that point, and then we get the stress at this particular point. As shown in the lecture, we verified that this stress is in equilibrium with the zero body forces vector. To find the traction forces on the boundary edges, we need to find the normal vectors on each plane. So NA, the normal vector on A, is equal to, we're going to, as shown in the lecture, we're going to do this in plane. So NA has component 1 in the x1 direction and 0 in the x2 direction. So this is the normal vector on the edge A. So let's just write normal vectors on the edges. The traction vector on NA is equal to the transpose of the stress matrix multiplied by NA. So the stress matrix, stress is equal to x2, 5, and we're only going to use the two-dimensional stress matrix. So the stress in matrix form has the form x2, 5, 5, x1, and the normal vector on edge A is 1, 0. The traction vector on NA is equal to the transpose of the stress multiplied by NA, and this is evaluated at particular values for x1 and x2, because on edge A, x1 is always equal to 2. So that's always when x1 is equal to 2. And TNA in matrix form. And here's the traction vector on A, which is equal to x2, 5. x2 is a variable because it's equal to 0 at this point and equal to 1 at the top point. So this is the traction vector on edge A. I'm going to put all the NB is equal to 0, 1. So all the normal vectors on the planes or on the edges, NC is equal to 0, negative 1, 0, and ND is equal to 0, negative 1. So this is the normal vector on the edges A, B, C, and D. The traction vector on the plane with of edge B is equal to, as well, the transpose of the stress dot NB, but that's evaluated for a particular x2, which is on this edge, x2 is always equal to 1. On the top edge, x2 is always equal to 1. And as well, TNA is equal to the transpose of the stress on NC, sigma transpose multiplied by NC, and this is evaluated at a particular x1, which is x1 is 0. This is equal to TNC. And TND is equal to the transpose of the stress multiplied by the normal vector on D, and this is at a particular x2. That particular x2 is equal to 0. And let's look at TNA, TNB in matrix form, TNC in matrix form, and TND in matrix form. And you should verify these are the numbers. These are the same that we obtained when we did this by hand in the lecture. Okay, so now the external virtual work is equal to, I'm going to just write the expression, external virtual work is equal to the external virtual work due to body forces. So external virtual work body forces plus external virtual work on edge A plus external virtual work on edge B plus external virtual work on edge C plus external virtual work on edge D. The external virtual work of the body forces is equal to the integration of row B vector dot u star, but row B vector is equal to the row B vector, the body forces vector is equal to 0, so the external body forces is equal to row B dot u star. Should be equal to 0, but I'm just including it here because in your assignment the row B vector is not 0. So external virtual work for the body forces integrated on x1 from 0 to 2, on x2 from 0 to 1, and on x3 from 0 to t. The row B vector for this particular problem is 0, and the u star is given as a multiplied by x1, comma 0. And because row B is 0, the dot product of row B and u star is 0, and so the external virtual work due to the body forces will be equal to 0, oh, u star, shift enter, this will be equal to, so the external virtual work due to the body forces is 0. And notice that the body forces was the external virtual work due to body forces was integrated over the whole volume. Now, the external virtual work due to the traction vector on A is equal to the integration of the force vector on the traction vector on A dot u star on A. So I need to evaluate u star at all the edges. So u star on A is equal to u star at a particular x1. A at the edge of A, x1 is equal to 2. So I'm going to copy T and A, T and B, T and C. And instead of T and A, I'm going to call this u star A. U star edge A is equal to u star when x1 is 2. U star B is equal to u star when x2 is 1. And again, u star C, u star D is equal to u star for a particular x1 and u star for a particular x2. Let's just look at them. U star A in matrix form, B, C, and D. Shift enter, and the displacements on each edge, the displacement vector on each edge are given as 2a, ax1, 0, and ax1, 0. So these are the displacements on edge A, edge B, edge C, edge D. Now the external virtual work is 1 due to the body forces. The external virtual work on edge A is T and A dot u star A integrated over edge A. Now edge A, this is edge A, has integration from 0. x2 changes from 0 to 1, x1 does not change, x3 changes from 0 to t. So this changes, x2 changes from 0 to 1, and x3 changes from 0 to t. The external virtual work on B, edge B is equal to B dot u star B. For B, I have x1 changes from 0 to 2, and x3 changes from 0 to t. For C, I have the traction vector on C and the displacement star on C. x2 changes from 0 to 1, and x3 changes from 0 to t. And for D, external virtual work on D is equal to T and D dot u star D, and x1 changes from 0 to 2, and x3 changes from 0 to t. The external virtual work on the edge D is the integration of forces versus displacement on edge D, the edge, the integration is conducted on x1 from 0 to 2 and on x3 from 0 to t, and x2 is constant. Shift enter, and here is this is the row B, the external virtual work due to row B, external virtual work A, B, C, and D. And indeed, if I calculate the external virtual work, which is equal to the sum of all the body forces, the A, B, C, and D, external virtual work, shift enter, is equal to AT. So I'm just going to print external virtual work equal to AT. Okay, now what about the internal virtual work? The internal virtual work, I'm just going to write it here just for you as a reminder, is equal to the integration of sigma on 1 multiplied by epsilon 1 1 star, epsilon star 1 1 integrated over the volume plus S2 multiplied by E star 2 2, and so on. So we have the stresses, we're already given the stress matrix inside the object, we need to calculate the corresponding virtual strain. So first, the E star, which is the virtual strain, is calculated using the gradient of the displacement. So I'm going to gradient of U star is equal to the table partial U by partial X. So I need to define X first. X is equal to X1, X2. The gradient of U star is equal to table D U star of I with respect to small xj. I is from 1 to 2 and j is from 1 to 2, and here's the gradient of U star in matrix form. As if you watch the lecture, it's indeed A000. And E star, the strain, is equal to half multiplied by the matrix gradient of U star plus the transpose of the gradient of U star. Shift enter, and indeed A star, the strain is the same. Now, the only non-zero strain component is A, and so I'm going to integrate the sigma on 1, which is x2, multiplied by epsilon 1 1 star, which is A. So I'm going to take the internal virtual work is equal to, let's just print it, internal virtual work is equal to it's equal to the integration of sigma on 1, which is the stress. We've already defined the stress matrix. So this is the stress 1 1 multiplied by E star 1 1 integrated over the volume. The volume of the plate is x1 up to 0 to 2, x2 from 0 to 1, and x3 from 0 to t. And shift enter. Indeed, the internal virtual work is AT, the external virtual work is AT, so they are indeed equal. Now, in this example, we have two different U stars. One is equal to AX10. The other one is actually equal to BX2. Everything is the same, all if I just make this 0. And the U star is equal to B multiplied by X2. So for the second one, I'm just going to put U star as BX2, and I have to, of course, clear everything. So I'm going to just quit everything, or clear all the variables. Everything is the same, but the internal virtual work is the integration of all the non-zero components of the stress with the non-zero components of the strain. Now, I have to sum the stress II or ij multiplied by the strain ij integrated, the sum, I is from 1 to 2, and j is from 1 to 2. These are all the different components. Shift enter, and indeed the external virtual work is 2bt, and the internal virtual work is also 2b multiplied by t. So in the second example, we have a simply supported Euler-Bernoulli beam subjected to the distributed load given, which is a linear load. It's a triangular load. We have Young's modulus, length, and moment of inertia as E, L, and I, and we need to verify the principle of virtual work. Now, as was shown in the lecture, the first thing we need to solve the beam to find the bending moment. And to solve this beam, we're just going to solve the differential equation. So I'm going to call the solution as S, solve the differential equation, as we've done this in the beam equation, EI multiplied by the fourth derivative of the displacement. This is equal to Q, and Q is equal to negative 5 multiplied by X. I'm going to making everything function of X. The boundary conditions are y of 0 is equal to 0. Y of L is equal to 0. And the moment, which is the second derivative of the displacement of 0, is equal to 0. And the second derivative, which is the moment at the point L, is equal to 0. And it doesn't really matter if I multiply by EI or not. Because it's equal to 0 anyway, but let's just to be consistent, I'm going to multiply by EI. So these are the boundary conditions, 4 boundary conditions. I'm solving for y in terms of x. Shift enter. I have to clear the variables because x was already given as a vector and it's still in the memory, so I'm just clearing x and y and s and all the variables that I'm using. And indeed here is the solution. And I'm going to capture the solution. Y is equal to y of x when I utilize that solution. Indeed, this is the displacement function of the beam, and the moment of the beam is equal to d EI multiplied by the second derivative of y with respect to x. The second derivative of y with respect to x is obtained by taking dy with respect to x twice. This is how the syntax is for in Mathematica. Or you could do it by taking by differentiating y twice. Oh, the symbol moment is protected, so I'm just going to make it m. M is equal to EI multiplied by dy with respect to x twice. So we have the bending moment diagram, the internal virtual work and the external virtual work. Let's remind you with the equations. The internal virtual work is equal to the integration of m multiplied by the second derivative of y star with respect to x squared, while the external virtual work was equal to the integration was equal to the external virtual work distributed load plus external virtual work reactions on beam. This is just to remind you. So let's calculate the internal virtual work. Print the internal virtual work equal. Of course, the y star, the virtual displacement is given as a multiplied by x squared multiplied by x minus L. The internal virtual work is equal to the integration of the moment, the second derivative of y star with respect to x twice. This is integrated when x goes from 0 to L. Shift enter, and here's the internal virtual work. The external virtual work is equal to the external virtual work due to distributed load plus the external virtual work due to reactions on the beam. As shown in the lecture, the external virtual work for the actions on the beam is 0. But in your assignment it is not necessarily 0, so you have to multiply the reaction multiplied by the corresponding displacements. But for this particular example, the external virtual work is only due to the distributed load. The distributed load is equal to -5 multiplied by x. Notice that I'm just using x as the variable instead of capital X1. So this is the displacement. So this is the load multiplied by the displacement y star. This is integrated when x goes from 0 to L. Print external virtual work. And indeed, the internal virtual work is this, external virtual work is this. They're both equal.